Hi, this is Alfawzia Nihar from At Home Tuition. Welcome to our session today. The topic that we are going to discuss in our today's video is differentiability. Now let's start with the definition of the differentiability. A function is differentiable at a point if it has a derivative there. In other words, the function is differentiable at x if this exists. Please read this one. Limit h tends to 0, f of x plus h minus f of x divided by h. This is somewhat very similar to mean value theorem formula. Am I right? Thus, the graph of f has a non-vertical tangent line at x comma f of x. The value of the limit and slope of the tangent line are the derivative of f at x naught. So this is the definition of the differentiability. So if these conditions are existing, then we can say a function is differentiable. But there are some conditions. A function can fail to be a differentiable at point if the following conditions exist. Let me list out them one by one. First important thing is a function is not continuous at a point. If the function is not continuous, then obviously it is not differentiable because one implies the others. Differentiability implies the continuity, continuity implies the differentiability. The graph would look like this when the function is not continuous at that point. So how can you make a tangent line here? So it is not possible. Am I right? So the function is not continuous at that point. Okay, now let's see the second one. In case if the graph has a sharp corner at the point, then it cannot be differentiable. I'll show you a graph example for that one. Do you see this graph? It has a sharp corner at that point. So it cannot be continuous and differentiable. And the third important point is the graph has a vertical line at that point. Do you see this graph? It's too steep, no? Yes, if this is the case, the function is not differentiable. So one should know the conditions which should exist for a function to be differentiable and the points that will make the function not differentiable. So after reviewing all these points, you can go into the problem solving. Now let me show you some examples and explain you how the function is differentiable. Please look at this example. In this graph, you can see broken lines. Hence, the function h is not continuous at 0. So, it is not differentiable at 0. Am I right? And I'll let you know a fact here. A differentiable function is continuous. This is an important theorem that will be applicable in problem solving under the topic differentiability. The piecewise function for sure says that the function is not continuous. So, it is obvious that the function is not differentiable. So here in this example, the function h is not continuous at 0. So it is not differentiable at 0. Here is the general fact. Differentiability implies continuity. A differential function is continuous. If f of x is differentiable at a point x is equal to a, then f of x is also continuous at the same point x is equal to a. Let me prove this theorem. I'm going to show you step by step. Since the function f is differentiable at a, you can prove this mean value theorem. So this definitely exists, the first derivative. So this can be rewritten as, hope you're clear with this step. This is okay because x minus a is not equal to 0 for limit at a. I'm just rewriting it. Now the right side of the equation can be equal to 0. When limit x tends to a minus a is 0. So 0 times anything is 0. So obviously the right side would become equal to 0. Thus the first derivative of f of x at a, I mean f dash of a is equal to 0. Hence limit x tends to a, f of x minus f of a is equal to 0. And if we add a constant f of a to both sides of the equation and if we use the law 2, we get limit x tends to a, f of x is equal to, which is the definition of the continuity of f at x is equal to a. For more detailed information about the continuity, you can refer a video on the topic continuity. Hence, I have proved that a differentiable function is continuous. That is, I have proved differentiability implies continuity. I started with the definition of the differentiability and step by step I reached the definition for the continuity. Hope you are clear with this theorem and the proof. In case if you get any query, you can let me know. Here is another example. F of x is equal to modulus of x. Absolute value of x can be written as negative x and positive x. Am I right? This one is x greater than or equal to 0. So from this example, when an important condition does not exist, this is not going to be differentiable. Please look at the graph. At x is equal to 0, there is a corner at 0, 0. Am I right? The picture is different to the left and right of 0, 0. Do you see that? Suggest we try left and right hand limits. So I'm going to try left and right hand limits now. I'm going to apply the definition. So limit h tends to 0 at the right side, f of h minus f of 0 is equal divided by h. So this will be equal to h minus 0. Am I right? H minus 0 divided by h. It means h over h. So limit h tends to 0 positive 1. So what will become? This will become equal to 1. Cancellation of h, okay, since h is not equal to 0 for limit at 0. But now let's try the other side, 0 raised to negative, the other side of the graph. So on the left side, f of h is equal to negative h. Am I right? So negative h, negative 0 divided by h. Cancellation of h, okay, since h is not equal to 0 for limit at x is equal at 0. So the right side would become negative h over positive h, which is equal to negative h. So this is equal to negative 1. Am I right? So compare the left side and the right side. Since the left and right hand limits do not agree, you can say that the definition does not exist. This condition does not exist. And so modulus absolute value of x is not differentiable at the point x is equal to 0. That's it for this example. Hope you're clear with this example now. This is the second case we discussed in the initially. Now let's see the third slide. Here is an example for that one. Here is the next example for the third case. The third important point we discussed at the initial video. The graph is smooth at x is equal to 0 but does appear to have a vertical tangent. Am I right? So for this function we can write the definition as, here is the definition. Now let's simplify this. 0 plus h is h. So h raised to 1 over 3 minus 0 raised to 1 over 3. 0 raised to anything is equal to 0 itself. So the top row, the numerator would become h raised to 1 over 3. Here you can use a law of indices. When the bases are same, you can just subtract the exponents. So after subtracting, you will get h raised to negative 2 over 3. Am I right? You cannot write a negative exponent. So if you want to change a negative exponent into a positive exponent, you just have to shift it to the other position. In case, if you get a negative exponent in the numerator, shift the term to the denominator so that the sign will change. In case, if you have a negative exponent in the denominator, you just have to shift it to the numerator so that a negative exponent will be converted or changed into a positive exponent. This is what we do to change the sign of the exponent. So here, I'm going to shift it to the denominator. So I get, as h tends to 0, the denominator becomes too small. Am I right? So the fraction grows without bound. Hence, the graph, the function g is not differentiable at x is equal to 0. So you must notice that when the denominator becomes too small, the fraction will definitely grow without bound. If there is no bound, we can say that the function is not differentiable at all at that point. So this is a good example for the third condition. Apart from the three reasons, I'm going to show few more examples. Please look at this figure, the floor and ceiling function. This function is not differentiable at integer values, as there is discontinuity in each jump. Am I right? But they are differentiable elsewhere. So this is a very good example for the differentiability. Here you could easily understand the points where the function is discontinuous and where the function is continuous. Here is another easy to remember example. Please look at the graph. This is the graph of a cube root function, x raised to 1 over 3 or cubic root of x. Its derivative is 1 over 3 times x raised to negative 2 over 3 by applying the power rule. Am I right? So at x is equal to 0, the derivative is undefined. So the function, the cube root function x raised to 1 over 3 is not differentiable. Hope you're clear with this example. Okay, now let me show you one more example. Here is another example. Actually, this is a graph of the function 1 over x. At x is equal to 0, the function is not defined. So it makes no sense to ask if they are differentiable there. To be differentiable at a certain point, the function must first of all be defined there. Am I right? So it's not defined here. So obviously, this is not differentiable there. This is one easy to remember example. And one more important example is from trigonometric function. Sine of 1 over x. Let me post that too. Here is the graph of sine 1 over x. As we head towards x is equal to 0, the function moves up and down very faster and faster. So we cannot find the value it is heading towards. So obviously this is not differentiable. Apart from the three important conditions, I have posted some examples like floor and ceiling function, cube root function, 1 over x function, and sine of 1 over x functions. Hope all these examples will be helpful for you to remember the concept of differentiability. In case if you get any query, you can let me know. See you in the next video. Have a great time ahead. This is all about differentiability. I'll be back with a set of problems.